Hello YouTube, this is Carlos once again with CHS Electronics. This is video 2 of the PIC18F67K40 development board. On this video we're going to talk about the components that were chosen for this particular board and why I chose them. And you might get to see a little video of the board being turned on, but for the most part the actual video of the board being worked or being put to use will be on the third video. Anyways, so let's begin here with the PIC itself. We have a PIC18F67K40. It is a 64-pin device and it has a lot of great features. Let me show you what it can do. Well, if you go to the data sheet, it's a very high performance microcontroller. Its max operating speed, which can be selected internally, is 64 megahertz. It's got a 2-level priority interrupt, so you can select high priority interrupts that will always be triggered no matter what, and then you have the low level interrupts which will be interrupted by the high priority interrupt in the event that high priority interrupt occurs during while a low level interrupt is being processed. So it's got a 31 level deep hardware stack. It's got 4 8-bit timers, 5 16-bit timers, which are actually very handy. It's got a power on reset, power up timer, brownout reset, and you can select the voltage that it'll put it into reset once it goes below that voltage. And it's got 128 bytes of program flash memory with 128,000 or 128 kilobytes of program flash memory, along with a 3,562 bytes of data SRAM memory. Not only that, it also has a 1 kilobyte data EEPROM with which you can program the code protection to any or all part of either your code or the EEPROM or all of it. So it does come in a low voltage package, where it'll operate anywhere between 1.8 to 3.6 volts, or you can get the standard TTL version, which would be 2.3, or CMOS should I say, to 5.5 volts. Temperature ranges include industrial, which is what I use, which is from -40 to 85 degrees Celsius, or you can get the extended version, which can operate from -40 to 125 degrees Celsius. That extended version set is probably going to be pretty useful if you're planning to use your device in, let's say, inside your car, when you're running in a car and it's summer outside and you're out and about in the streets and your project is installed in your car, and you can pretty much be rest assured that it will operate well in high heat temperatures. So moving on, it has a this doze. I mean, it's not like a full sleep, and then you can pretty much set it to kind of halfway asleep. Idle is just doing there waiting for something to happen, and sleep mode is when you completely turn off almost all your peripherals, and you can conserve your battery if you have it using under battery power. So extreme low power mode, 500 nanoamps typical at 1.8 volts, and a sleep watchdog timer of 900 nanoamp typical at 1.8 volts as well. So that's when you put it in extreme low power. That's probably when you're putting it into hibernate of some sort. So that's pretty good. Talk about the peripherals. It's got a complementary waveform generator. It has within that generator, it has a rising and falling edge deadband control, full bridge, half bridge, 1-channel drive, with multiple input signal sources, so you can trigger it from multiple places. Got a capture compare with a PWM, 5 of them, and they come with 16-bit resolution for the capture compare modes and a 10-bit resolution for the PWM mode. So that's pretty good. It's got two 10-bit PWMs. Serial communication. Now this is one of the reasons why I chose this chip. This particular chip has 5 enhanced USART ports. So a lot of the older picks or the previous picks, they come up with up to two USARTs. So I think with this one, with 5, you can pretty much do a lot of communicating with this chip through a lot of those ports, and you can receive in one port and directly buffer it out to another port or to 2 ports or whatever. So this makes a great communications chip. So like pretty much all chips, it can handle RS-232 type signals and RS-45, and of course they're LIN compatible. Now unfortunately, it only comes with one SPI port and one Expert C SMB bus PM bus compatible. It's got up to 59 I/O pins and only one input pin, and that's usually the MC clear pin, which is only used for reset. So they are all individually programmable. They all have individually programmable pull-ups. They have slew rate control, which means that you can determine how fast your output pin can go from 0 to 5 volts or 5 volts to 0, and that's great when you want to slow down that rise time and you want to eliminate the ringing on your output pin because you're trying to drive like a high capacitive load. So that's good. It's got I believe like 5 ports that are interrupt on change, and on these interrupts on they also has an an input level selection control, so you can determine if you want to trigger or be sensitive to CMOS level inputs, or you want to be outputs, or you want to be sensitive to TTL level outputs, which as everybody knows, TTL level outputs only go about as high, maybe to drive something a fair load. They don't go up very high. They don't go up to CMOS levels. They only go up to maybe 3.7, 3.8, maybe even 4 volts if you have a load. So that's good. So you can talk to other to TTL devices and not just CMOS devices as well. So it also comes with a programmable CRC with memory scan, and it says reliable data program memory monitoring for fail-safe operation. It can calculate your CRC values for you, and it's apparently it's high speed and or a background operation, so you can either do it within your code, or you can have it run in the background, which will probably run at a slower speed. The hardware limit timers. These timers can be activated by some hardware pin within the PIC or externally to the PIC, which is very, very handy. Peripheral pin select. Now this feature is it wasn't very clear to me at first as to how you're supposed to set it, but apparently you can set your peripherals or whatever device you're using, like say for example the analog, the USART. You can redirect your input and output pins to any pin within a port wherever that particular USART happens to be at. So if we take USART 1 and we redirect it to let's say pin 6 and pin 7, where it's normally found at pin 1 and pin 2, you can do that, or you can set it to any other pin within that port other than the default pin 1 and 2, and this is just for example. So that's great. You can redirect any module within the chip, or any module, any function within the chip, and you can redirect it to any port pin that is within its port, and that makes for design really easy and really good. Now it takes a little bit more effort on the code side, but it makes for laying out your board a lot easier. Now it has a data signal modulator, which I haven't used, but that sounds pretty handy, and that's just basically combining two logic signals to modulate the data and encrypt it, which that's one option you can use it for. It's got two signal measurement timers where you can measure which comes with a 24-bit timer counter with a prescaler and multiple gate and clock inputs, so that you can measure a signal with a 24-bit resolution, and you can have it triggered by multiple gates, meaning external sources or different clocks. So now moving to the analog side. The analog side is it only has a 10-bit analog to digital converter, but it has a lot of functions that you normally would handle in code, and it automates that process for you. So it comes with 47 external channels. It can make a conversion during sleep, and also has 4 internal analog channels, meaning you can read analog values somewhere from 4 different places within the chip, and it can be triggered. For example, if you have it to trigger if an analog voltage reaches, say, that it'll trigger anywhere from above 0.2 volts or higher, it'll trigger the read on that once it passes that threshold. So it can handle your math functions. It can do averaging, filter calculations, oversampling, and threshold comparison, which is very handy and allows you to free up your code so that you can handle other things besides running the analog to digital converter. And it has an 8-bit hardware acquisition timer, meaning that you can set it to trigger with an 8-bit counter within the analog module. So it's got also has a hardware capacitor voltage divider, which you can use in conjunction with the analog to digital converter to pretty much use it as a capacitive touch sensor. So this voltage divider comes with 8-bit pre-charge timer, which it allows you to discharge your input pin either charge or discharge, meaning that you can connect it to VCC or VDD, or should I say VSS, for a determined amount of time set by your pre-charge timer. And what it does is either discharge or charge your input capacitors before you take an actual reading. Now I didn't understand why you would need to do that, but as far as connecting it to the voltage source, but you can connect it to ground or have it connect to ground, and you can discharge whatever capacitor you have at your input of your ADC, and that way whenever it's ready to take a reading, that input capacitor has already been charged to the original voltage that you needed it to do. So that's done with the adjustable sample hold capacitor array, which it has, or you can add more to it. And discarding the digital output drive circuit, that's the one that actually sends your input pin to either VCC or VDD, or to either the 5 volts or the ground, so that you can either charge or discharge the capacitance that's there at your input pin, and have it reset to to the default value that you need it to be before you make your measurement. Now, the zero cross detect circuit allows, as self-explanatory as it is, it allows you to detect when an AC signal on a pin crosses ground. So that's pretty useful, but it does not mean that you can actually connect it to an AC signal. All it means is that you would need a trigger that can sense that zero cross, and then it'll tell you when it'll send a digital signal to your pin, and it will either start a timer or stop a timer depending on how you have it set up, and it will trigger an interrupt for you to do something. Now, as all the PICs that I've seen, they all come, well, not for the majority, they come with a 5-bit analog to digital converter, which I never use, but I'm sure one of these days somebody will make use of it. So that DAC is the output is available externally, and it's programmable with a 5-bit voltage from either 0 volts to VDD or from the voltage references that you select. It has also internal connections to the comparators, to I believe the 2 comparators that are already within the chip and the ADC. So you can tie all this stuff together and you can make it work to your advantage. It comes with 3 comparators, with 5 external inputs, and of course any of the input can be routed through your peripheral pin select module, which allows you to determine what input and what output goes to which and what module. Very handy. Your fixed voltage reference module contains a 1.024 volts, 2.048 volts, and a 4.096 volt output levels. And 2 buffered outputs are buffered. One for the DAC and comparator, and one for the ADC. So that's actually pretty good. So moving on to the clocking structure, you have a high 1% precision, 1% calibrated precision internal oscillator that can go up to frequencies of 64 megahertz. You can select anywhere from 1 to 64 megahertz at any one of those levels you want. Or you can select a 32 kilohertz low power internal oscillator, or you can select an external crystal oscillator, and that's used for other modules within the chips. Or you can select your external high frequency oscillator, and you can use a 4 times phase lock loop to run that, and you can select, for example, an 8 megahertz clock, external clock, and you can connect it to your phase lock loop, and you can generate 64 megahertz out of there, or 32 megahertz, sorry, should I say. So it's got a clock monitor. In the event that your external clock source stops working, it'll switch from the external clock source to the internal clock source, and therefore your application can continue to run. The oscillator startup timer times out if you have it set to when your external oscillator or the internal oscillator is ready to go, and it will create a flag and letting you know that your oscillator is ready for use. Now, as with all PIC microcontrollers, they all come with the in-serial circuit programming, at least these newer models, these flash versions. They all have the in-circuit debug, and it's all integrated within the chip. Now, this particular chip, like I said, comes with 128 kilobytes of program memory, 38,568 bytes of data SRAM, 1 kilobyte of data EEPROM. It's really 59 input-output ports with 1 input port. It's got 3 comparators. It's got 47 ADC channels, 1 5-bit DAC channel, 1 zero cross detect module, 5 CCPs, which is capture, compare, and PWM modules with two 10-bit PWM modules, one complementary waveform generator. Can't remember what the SMT, signal measurement timer. There we go. Two signal measurement timers. One low voltage detect module. One 8-bit four 8-bit timers with a hardware limited timer, and they're all. It all comes with a window watchdog timer, which as everybody has, if anybody's ever used a watchdog, you have to reset your watchdog prior to timing it out, otherwise it'll reset your microcontroller. And this is in the event that something happens within your code that causes it to freeze or lock up, and then instead of it sitting there doing nothing, the timer runs out, reset your device, and then you keep going from where you left off. Well, I guess you start over. You don't really keep going from where you left off. It's got a CRC module, 5 UARTs, which is very handy. Oh, it's got two I2C SPI ports, so that's great. Module, should I say. It's got two I2Cs and two SPIs, and all the output pins of every module are they're pin selectable, so you can send them pretty much to any pin on your port, on whatever port they correspond to, except for your ADCs, your analog to digital converter pins. All the ports on this PIC have, except for one or two, but I believe all of them have ADC on each port, an ADC module on each port. And you can't change, say, analog pin 0, and you can't change it over to pin 7. So pin 0 stays at pin 0, pin 1 at 1, 7 7, so on and so forth. But that's no problem. That's very easy to handle, and you can select the whole port to do an analog to digital conversion, or you can just select one out of each port. So the peripheral module disable, that is very handy when you want to save power, or you want to make sure that whatever peripherals you're using within the PIC are not, for one thing, consuming power, or two, getting in the way of other peripherals or other functions within the chip, and they prevent them from working properly. So you can disable all these functions or peripherals or modules that perform certain functions. You can disable them and not have to worry about clearing the registers or doing anything with that. Just makes programming a little easier. It's got an internal temperature indicator, which you can send out to any of your pins, and you can read it either through LCD or OLED or anywhere. It's easy for the programmer to access that information and make decisions based on it. If it's running too hot, you turn on a fan or something, like that. And it all comes with one, of course, one debug output. Now, this particular family of chips has, it's got brothers and sisters, which some are very similar, but the differences would be either in the program memory, or the data SRAM, or the data EEPROM, or the IO pin count, which I use the 67K40, but as you can see, all these other ones here can also have similar functions or features that the one I'm using here now has. So this is the pin diagram of that particular chip, and this is right here. This pin right here is the only pin that is input only, and that one's the pin that's used to program it or to put it into reset. So okay, that's this particular device, and of course that brings us back to the schematic, and that's the gist of this chip. Now, moving on to the next one, we can go to the level shifter, which is the TXB0108 PWR. Now this particular chip is, as the name implies, an 8-bit bidirectional voltage level translator with auto direction sensing. Now this particular chip could have been replaced by, say, 8 MOSFETs and N-channel FETs, and pull up resistors on either side, and we could have just made voltage translators through that. But I think that would have been a lot more space on the board, and it would have not been very practical to try and put 8 N-channel transistors in this area, along with 16 resistors to go with it. So I decided to go with the chip and make things a lot simpler, and basically that was it. It was one of the easiest things I've used so far. So this particular chip has 2 input-output ports, and one of them is 5 volt tolerant, and the other one is up to 3.6 volt tolerant. So there you go. This is one typical application block diagram where you have a 3 volt processor here and a 5 volt peripheral here, and you can have them communicate with each other and everybody be happy. So moving on to the next device, we have here the NRF 2.4 gigahertz module. Now that module here is where, I don't have a data sheet for the module. Well, we'll come back to that here in a minute. So let's move on to the Bluetooth module. The Bluetooth module, on the other hand, is just a standard HC05 Bluetooth module that you can get from pretty much anywhere. This particular data sheet that didn't actually come with the one I bought. I had to go find it at another website. Actually explains this particular module very well, and it gives you a few sample schematics as to how you could connect it with your microcontroller, or how you can connect it pretty much to any device that uses the UART to communicate with the module. So in this case, the commands here are pretty much straightforward. It's using AT commands, so it's very, very easy to use. And as a matter of fact, I didn't even have to touch anything within this module. I didn't have to send any commands or anything like that. I just plugged it in, powered on, started transmitting data out my UART at 9600 baud, and I can transmit out to my phone and have it communicate like it's supposed to. So I didn't have to do anything with it to get it to work. It just worked right out of the box, if it came in a box. So moving on, we go to our FT232RL, which is our USB chip. Now well, I guess I don't have that one in here either. Why don't we go to Mouser and see where that's at. So the USB chip. The USB chip is also very easy to use. You don't have to download any drivers. You don't have to do anything. The Windows automatically recognizes it when you use it, and it allows you to communicate at any baud rate that you want. So this is the internal block diagram of what it comes with. There's a lot of stuff, but you won't even have to use most of this stuff. The only things you would have to worry about are probably your connections. and how you connect it to either the USB or your microcontroller. So this is a typical application. This is basically how I have mine set up, except that not only of having a ferrite bead, I use a blocking diode to prevent back voltage coming in from VCC and going back out into my USB port. This is one area here, the test pin, that on one application I did not connect it to ground. Now luckily there was a ground pin right next to the test pin application, and I just bridged it with some solder and made it work. Otherwise the chip was not responsive, it didn't work well, I couldn't get it to communicate right, and that was because this particular test pin was not grounded. So here's a self-powered application. Mind you, VCC is connected directly to your circuit board power supply, and it's not connected to the USB connector power that comes in on pin 1, but that power is used to bring the device out of reset whenever it's plugged in. Otherwise, when you unplug it, this the 10K gets pulled to ground, pulls this pin to ground, and it sends the device into reset, and it won't work, and it won't draw any power. I always leave mine connected. I don't I power it at all times. I never leave my pins here at high or low, or both of them high when the device is powered off. I always make sure this device stays powered, because I am actually sending power through these pins into the device. So yeah, these chips are pretty pricey, but they work really well, and I like them. I just wish they were a little cheaper and perhaps even a little smaller. And I haven't needed to use any of the software that you can download from FTDI to actually communicate with this particular device itself and make use of your I/O pins over here, which you can, but I don't need to. All I need is a USB translator or interface, and as far as these other pins, I don't care to use them. I always use my microcontroller to do things that I want to do. So anyways, moving on to the next device is of course my all-time favorite, TM1620. In this case it's the version 1. Now I don't have the data sheet for that open just yet. Give me 1 second and I will open that up for you. Now I really like this display driver. Yeah, I know it's in Chinese and it doesn't make for anything good because it's written in Chinese. The data sheets are written in Chinese, but you can get a fairly good translation of it and you can make it work. In the previous video I've made where I designed an LED matrix board using this chip, I give a timing diagram with the commands and in what order you need the commands to send the commands to get this chip to work like a champ. I have not had it failed using the code that I've been using because I actually understood what we were supposed to do within this data sheet and made it work really good. So if you guys have any question on this particular type of chip, then you guys can send me an email or leave a comment, but and I'll try to help you as best I can. So from what I've seen, all the other devices that are similar to this TM1620, they all pretty much looks like they follow the same format. You have to send the command 1, command 2, command 3, and then the rest of the bytes of your data. And if you want to send any more commands, you send more commands. But I think the 16 TM1628 and I believe the 60 TM1638 I believe is another one. I believe they all follow the same format, and they all include this little filter circuit here at the inputs, which I don't normally use, but I know some people that do. So I like this chip. It's not easily available here in the United States. You have to order it from China, but they are really cheap and they work really well. So we move on to, well, I think our displays. Our displays are, of course, the in our case is the 4301 ASR. All you really need is the 4301A. Well, in this case, the SR stands for the super bright red, but the base number is the 4301A, and that's for, I guess, common anode, I think, if I remember right. No, it's common cathode for the 41A, and the 41B is the common anode, which kind of makes sense if you put it the other way, but not this way. So these are really good. I like these. They're pretty expensive though. I mean, it was like $9 for a set of 4 or 5 from Amazon, and I don't know why they're so expensive, but I'm sure we can find other cheaper models or different types. And as you can see, they come in red, green, yellow, and I know I've seen some in blue, so that if you want to change yours to blue, that's excellent. So moving on to the next component, this one here, the NPIC6C595PW. Now this particular device is a variation, or should I say it's a what is this company's name? Jeez, I forgot. An Xperia's version of the TPIC 6C595, or the 595 serial in parallel out shift register. Now this particular device is really small, which is what I liked, because I've used a similar device that is the N, so it's the big chip, the big through-hole pin chip, and it's pretty big, but it can handle, you know, it's a half a watt chip, so it can handle quite a bit of power. It'll handle up to 50 volts. The outputs itself are open drain, so you can put a max of 50 volts before the internal transistor gets damaged. And they're great for driving LEDs or relays and any medium current requiring device. You know, anything from up to I believe 500 milliamps for the PDIP package, which is the big chip. But I think this particular model here, I think it only does 200 milliamps. Oh, here we go. Source drain diode current. Continuous is 250 milliamps if you want to continuously sync 250 milliamps, or if you want to pulse it at a small, well, in this case it would be 100 microsecond pulse, you can sync twice as that. Now if you want to turn all your outputs on, you can sync a maximum of 100 milliamps per input, or per output if you want to turn them all on. And if you can do them all on at 250 milliamps, of course you can only pulse them each output at a time, or outputs on. So this is very, very good. I like this chip. I'm going to be using a lot of these simply because they are small. and they can handle a lot of current, and they're open collectors. So here is two of them. This one here drives these relays, and then this one drives these LEDs, this bank of LEDs over here. So I recommend you guys, if you guys can do some experimentation with the plastic dual inline package of this particular device, or one very similar to it, which is the 595 serial in parallel shift register. They're easy to use, they're very fun to use, and you can make them work. So there's another one here. Now let's take a look at these relays. The relays are, here we go, they are very small, not too small. There we go. Whoa, Nelly, there we go. Now you can get these relays in the through hole or the SMD version, which, if you look at the two, the only difference is that these pins are just bent out. It's the same component with the pins bent out, so that you can do it that way. You can surface mount them. Now these they come in a up to 24 volt power range, from 3 to 24 volts, and the ones that I have on the board are 12 volts. So the only reason I use these particular relays in the 12 volt range is because I had quite a few of them lying around, and I wanted to start using them for some kind of project. Now these, being that they're small relays, they are for small signals. They're not meant for anything greater than 30 volts DC at 2 amps. And as far as an AC signal source, it does not say not to use with any AC signal, but I think a small AC signal, which by that I mean like an audio signal, you know, like a 10-15 watt audio signal, maybe maximum of 50 watt audio signal. They're good for that, for switching audio signals, if you want to make like an audio signal switcher or anything like that. But I don't recommend using these relays to switch mains voltages anywhere above, 25 volts AC, and I don't think you're doing good by doing that, because they are not rated for that. Now it says you can switch 110 volts DC at 1 amp, but that's only if it's a resistive load. You can switch 220 volts DC, but only if it's a resistive load. So the maximum power dissipation is 30 watts for DC voltages. So you have to consider that whenever you're using these relays. Now these particular relays, I like them. They're small, they're very compact, and here they come in a single side stable, and then they have the one coil latching where you can set or reset with the polarity of the pins. These will be more expensive, the latching ones, but let me tell you, they save power in the long run. The ones they install now are not latching, so therefore once the relay is turned on, you're consuming power, and once you turn off the relay, no power is consumed, but the contacts switch back to their normally open position. So those are the relays, and now moving on to the power supply section, which is these two voltage regulators. Now these regulators are both from the same family. There we go. They are low dropout positive regulators. They come in, they're available in a 3.3, 5 and 12 volt or adjustable versions. Output current maximum is 3 amps with a line regulation of 0.015% typical and a load regulation of 0.1% typical. So to me that sounds like they're saying that these things are pretty stable up to 3 amps. So you should have a change in voltage output by 1.1%, but that's what they're trying to say. But in reality, that's not the truth. A lot of these devices, the load voltage the output voltage will drop maybe 100, 200, up to maybe even 300 millivolts when you start loading them down past 1 amp. Well, on these, in this particular device, it's just a 3-pin device, and you can. This is how you implement the adjustable version, which is very similar to the LM317, with an input cap, an output cap, and your 2 bias resistors. I don't use tantalum capacitors mainly because they are very expensive. I tend to use the low ESRs. On all my projects, I use low ESR capacitors. The lowest I can afford. So anywhere from a 300 milliohm or less capacitor is best. The lower the milliohms, the higher the cost. Well, this wraps up this portion of the video. Let me see about showing you guys the unit just powered on. And oh, before I forget, the fuses. I use 5 by 20 millimeter fuses. They come in a wide variety of sizes, anywhere from 0.1 amps to 15 amps. Now these are very useful because they're small and they are good. Let me show you the data sheet. Here is the cartridge fuse by Little Fuse. Now they are expensive here at Walmart. At Mauser. If anybody can order in bulk fuses, and I mean quality fuses, I suggest you go to a company called TTI. TTI sells their fuses at a much better rate than Mauser. Mauser's let me just click on this link here. Mauser's prices, for example, you buy one, you pay 51 cents for it. You go to TTI and it will probably be very similar, but the difference comes in the quantities that you buy them. So they have 4,150 in stock. Let me find one that isn't. Let me see that if it shows you. Here we go. So let's look for the other one. Its counterpart, the MXP, which is basically just a packaging count, and it still gives us the HXP or the MXP, which is the same part. It's just one determines how many components come in the bulk, when in bulk packaging. So, well, this one doesn't say exactly what I wanted it to say, but if you buy at 100 or more, your prices will drop considerably, say 25% a piece, 25 a piece instead of 34 cents a piece. So Mauser's is good for finding a lot of what you need, but TTI in this case is if you're going to buy in bulk what you need, which is what I use whenever I buy a lot of bulk. I don't go to China directly, or Alibaba, or AliExpress, or Banggood, as a lot of YouTubers do. I like to know that when I buy my components, they are quality components, they are true components, and they're not fake components. Yeah, they cost more, but at least I know that what I'm getting is a real and not a fake. You know, no fake news here. So that's for the, at least that's for the semiconductor components, like diodes and things like that. Chips, resistors, because they're not all made the same. ICs. Now the connectors on this board, I buy these at where did I get these? Amazon. Now they come in a 10 post, 8 post, 12 post, 14 post, 16 post. So they have a variety, and their lead spacing is 2.54 millimeters, which is 0.1 inches. And that's your standard size, width, or spacing on breadboards and things like that. You know, your headers, they're 0.1 inches. So I buy them here because, well, they're pretty much the only place I can find these things that are you know, fairly cheap. Although in this case I paid $19 for a 20 piece of the 8, which is, I guess, $1 a connector. That's still pretty high. You know, anywhere like 25 cents per. If I buy maybe 50, that would have been great, but being that this is my first run, I'm okay with paying $19 for 20 of these. So I on this particular board I have the 8-pin, and I also have the 6 pins. Well, the 6 pins are for the my power output, my ground outputs. So I have a 12 volt ground, a 12 volt power output, a 5 volt power output, and a ground output, and those are located above the relays. I mean above the fuses next to the relays. So here's a 1 6-pin, here's the other 6-pin, and the other one. So let me zoom in here so that way you can see I have my 12 volts, my 5 volts, and my ground. And you can jumper these to any one of these 8 relays, and you can either switch the ground or switch the 5 or 12 volts, depending on your application, of course. Now the fuse clips, let's see if we can get nope, wrong way. Get a part number on that, because apparently I didn't have that ready for you guys. No. I usually, where do I have that darn fuse clip? Well, never mind the fuse clip. I'll come back to that and on the next video. Well, pretty much this is the video. This is description of the components, and give me a minute and I will show you a few things of the board and a piece of software or an app that I've developed to have control of this board and set my individual pins high or low, or turn on my my analog to digital converters, or my interrupt on changes, or things like that. And you can see that I can control just pretty much about everything on this board. Now the only thing I haven't gotten working yet, and that's only because I haven't started it, is I haven't started the communication with my my Nerf radio. Now with that I need 2 nerves, and I have 2 boards, but I'm waiting on fuse clips to come in, because I don't have any fuse clips on that particular board, on that second board, and so I can't really power it, you know. Although I could power it through the USB port, but the 3.3 volt regulator is not is not tied into, see, let me see, where's the USB port? Okay, so we have the USB port power come in, comes out over here, and it comes and it ties into this 5-volt regular output, and therefore I don't have a direct connection to the 3.3 volt regulator to also turn on that 3.3 output line, and therefore not being able to do that, I can't power the radio on that second board because I don't have any 3.3 volts. So that's that. So let me just show you these boards and I'll be back here in a minute. Well, here we are. This is just a small clip, a small video of the board at work, and well, before we begin that, I want to show you, just maybe give you a better look as to how it looks, how the layout is. See if we can get this thing to focus. It looks pretty good. There's my Nerf radio and my USB module right there with all my fancy little low ESR capacitors and the little relays, of course. Anyways, let me plug in the USB so you can see that I can plug it in, but I won't get any power to the module, to the USB modules. I don't have any power here. There's no lights on, and so let me get turn the power on to the 12 volt input right here. Let me just turn on that power, and there we go. So now we have our red blinking light for our Bluetooth module, and all that does is indicate that it is not paired, but once it gets paired, it'll blink twice, and then the other LED, which is orange in this case, will be on all the time. It'll be solid. So we got a little a blown fuse LED, well, a good fuse LED, and then we have our two power LEDs. So we have that one's for 3 volts and 3.3 volts, and this one's for 5 volts. So if this fuse blows, these two will turn off, and also this one as well, but this one is fused to our 12 volt output so that we can send 12 volts out to the relays, and we can protect we can protect those outputs with the fuse. So anyways, this is the program that I've been developing with Visual Basic. It is very, very long, and I think this is probably one of the longest pieces of code I've written for a computer. Mind you, it's only Visual Basic, but hey, you know, I'm not that good at programming computer stuff. Also, let me show you what the layout of that particular program is. So, as you can see, it's just one big sheet or one big page, and I have buttons for relays, buttons for port A, buttons for port B, port C, port E, and port F, and then I have my LED relays. And then I have a section here where I can see what I'm sending as far as commands, my in text version, and then I have my my buttons that allow me to connect to the Bluetooth or the radio, the Nerf radio, and then my clear button down here. So let me just turn that on and give you a little sample as to what it can do. So as you can see on this one, the button appears red, and we can see closely it says click to connect to development board. But if we move over here, you'll see that it's already connected to the development board. So as soon as this program starts, it'll pull the serial ports and ask to see it'll check to see if the development board is connected. And as you can see, the text it sent my commands, my polling commands twice, and then it received a connection established transmission from the board. So everything is done in ASCII format, so that anybody can just type any commands to the boards with their keyboard and not have to rely on this. So I'm going to turn on one relay, and there it is, and I'm going to turn it off again. So all it does is you toggle the input, and as you can see, I send a command and I receive and acknowledge. So let me clear that, and here's sending the command up top and then receiving and acknowledge on the bottom. So there's that. Let me turn on one LED. Here's my LED button, and there is my LED, my yellow LED. Now I can turn them all on using this button, or I can turn on all the ports using their respective buttons. So just to give you a little, I guess, an understanding of the layout here. This is our relay section. Then we have our port A output control. With this port A, we can have it to be bistable, meaning we can have it on or off, or we can select 100 millisecond pulse to send out, or a 500 millisecond pulse, or a 1 second pulse, or a 1000 millisecond pulse. Now I won't be showing that today. That'll be the next for the next video. And then our port B section is our analog inputs, so we can enable or disable our analog inputs, and that's for all the port B analog inputs. And as well, we can select them all at one time, or we can disable them all at one time. As far as port C is concerned, these are our interrupt on change. Right now, as is, there's no interrupt on change, no edge interrupts selected, but we have a positive interrupt edge, or we have a negative edge. And if you select one, click it, you can also select the other one and click it, and then you'll have both interrupts enabled, so that you can trigger off a negative and a positive going edge. And of course, if you select none, well, then you disable those interrupts. Now port E and port F are just basic on-off selections. So it's either at 5 volts or it's at 0 volts, and that's all they do, until of course I'll add more functionality and I'll enable other features within the chip. These buttons here are to enable the Bluetooth programming, so that you can talk directly through to the Bluetooth by typing in commands, which is in a section that I have not yet included, but it's going to be for the final product. Also, it has send data to the NERF radio. So in other words, right now we're communicating to the board, but if we wanted to, we can pass that same information over to the NERF radio by clicking this button. And now whatever information we send from here, the NERF radio also receives. And also the same goes for the Bluetooth device. If we connect this one, we can send whatever data we send here to the Bluetooth, and so basically the Bluetooth device would be listening on us or on what we're doing. And then if we wanted to, we can receive the information that the Bluetooth or the NERF radio is transmitting to the board, and we'll just get a copy of that here. So effectively, this button enables this software or this application here to become a sniffer, I guess you can call it, or a spy, or listen in on the communication between the board and the radio devices. Well, anyways, that's just a quick little demo of what this board can do so far. Again, this board is mainly developed to to allow a programmer to do pretty much anything, or anything that they can do with, that's limited by their imagination. I didn't show. So whenever I send a command, you noticed that the commands are also being displayed here. Well, let me clear that, and now let me come down here, and every time I send a command from the application, I see the command. So right now it's U1R010, and that is the command, and every command is sent in ASCII format. Again, so that anybody can use a computer keyboard and talk to it through USB, of course. Now this is the pot for the analog to digital converter section, which is on port B, but this will be for the last video. So I want to thank you guys again for joining me, and I hope you guys liked this video, and I hope you found it interesting. And these will be out on the market pretty soon, as soon as I get everything else verified and make sure that everything else is working as it should. And then we'll put a link on the description or within the video, and let you guys know where you can get more information on these boards. Anyways, thank you for joining me tonight or today, and hope you guys have a good one, and we'll see you guys on the next video. Thanks again.